Hi, my name is Amira and I'm going to explain about summary for this project. This project explores the design of a processor architecture specifically optimized for online gaming applications. The focus is on achieving high performance while balancing cost and power consumption. The project utilized various techniques and concepts. The first one is performance goals. Second one, workloads and benchmark. Third is CPI equation. Fourth is Amdahl's law. And the last one is optimization and decision making. The first one is performance goals. The team defines specific performance metrics for mobile gaming, including high graphics performance, low latency, power efficiency, and cost efficiency. The second one is workloads and benchmarks. Benchmarking data for the Qualcomm Snapdragon 8 Gen 3 is analyzed, comparing it to its predecessors and other processors like the Apple A17 Pro. The results highlight the processor's performance in diverse workloads, including gaming, AI or ML, and multimedia. The third one is CPI equation. The project thoroughly analyzed the CPI, which is cycles per instruction, equation to understand how different aspects of the architecture affect its performance. This includes analyzing the impact of instruction set design, pipeline depth, and memory system organization on gaming performance. The fourth one is Amdahl's law. The project applies Amdahl's law to predict the potential speed-up achievable by parallelizing the program's workload across multiple cores, showcasing the importance of optimizing both sequential and parallel sections for maximum efficiency. The last one is optimization and decision making. The project explores several design trade-offs, including CPU-GPU integration, memory hierarchy optimization, custom ASIC's power management strategies, thermal management, and pipeline optimization. These choices are crucial for achieving balance between cost, power consumption, and performance to satisfy the demanding requirements of online gaming applications.
Hi, I am Shafika. I'm going to talk about CPI equations. CPI stands for cycle per instructions, which is the number of clock cycles that required to execute an average instructions. So, analyzing instruction set designed for mobile gaming using CPI equations, the formula is CPI equal to sigma bracket instruction mix multiplied by cycle per instructions and bracket instructions equal to 30%, meanwhile memory instructions equals to 40%, and then control instructions equal to 20%, and then last one, floating point instructions equal to 10%. Okay, next, assume the cycle per instructions by referring the table below, which is we got instruction arithmetic, memory, control, and floating point. You can refer the table for the different cycle for CISC and RISC. So for the equation calculations, we use the formula given using by how many cycle they got. CPI for SISC is 3.2, which is higher than RISC at 1.6. So here we can conclude that CISC architecture is more complex than RISC. For the Snapdragon 8 Gen 3, we use RISC as the main architecture, indicates that better performance, especially for mobile gaming.
I am Ainadira, will be presenting you analyzing processor pipeline for mobile gaming using CPI equation. So guys, what is pipelining? Pipelining is a technique used in CPU to divide instruction process to a few stages, allowing multiple tasks to be processed simultaneously. There are two types of pipelining depth, which is basic, contain 5 stages, and deep, contain 10 stages and above. So these are the formula to calculate CPI depth, which CPI depth equal to CPI ideal plus miss prediction multiplied with miss penalty. Let's compare both depth, which one suits Snapdragon 8 Gen 3. Okay, let's assume for basic stage, the CPI ideal is 1, branch miss prediction rate is 10%, and branch miss penalty is 2 cycles. So we calculate using CPI equation and we will get 1.2. While for deep stage, we assume that CPI ideal is 1, branch miss prediction rate is 10%, and branch miss penalty is 3 cycles. So when we calculate using CPI equation, we will get 1.3. We can conclude that basic stage pipeline have lower CPI than deeper pipeline. Well, we can say that basic stage execute instruction effectively, while deep stage use high clock speeds and complex in executing instruction. Lower CPI promoting better processors performance for mobile gaming. So, the Snapdragon 8 Gen 3 most likely use a balanced pipeline depth to maximize efficiency, reduce risk, and improve responsiveness, which led to a flawless mobile gaming experience.
Hi, I'm Nadia, and I want to continue the CPI equation about memory system organization for mobile gaming. So if you can see here, is the formula CPI equation for system memory organization, where is equals to CPI base plus in one bracket miss rate L1 times miss penalty L1. So does with L2 and L3. So usually miss rate for L1 is between 3 to 5%, and for L2 between 2 to 4%, and for L3 is less than 1%. Okay, so let's look at the example, and let's assume that CPI base equals to 1. So if you can see here, this is a table where have level, miss rate, and miss penalty. For it's easy to use in the formula. Let's answer with the formula given, where CPI memory equals to 1. 1 is the CPI base, and plus L1 miss rate and L1 miss penalty, where in the table we see the L1 is 5%, so you convert to 0.05 times 10 cycles. So that's L2 and L3. So the equals is 2.32. So what do we get when we use the CPI equation for system memory organization, where we get the base CPI increase from 1 to 2.32, and it also improve processor performance. And if the processor increases, the size and access time of the memories increase. So the SNAPDRAGON agent integrates a sophisticated memory hierarchy with fast caches to minimize memory access times, hence reducing CPI for a better processor performance and impressive gaming experience.
Hi, I'm Aina and I will present my part which is Amdahl's law. So what is Amdahl's law? Amdahl's law is a formula that predicts the potential speed increase in completing a task with improved system resources while keeping the workload constant. So here Amdahl's law formula, which is Pi equal 1 divide bracket 1 minus P plus P over N. So P stands for the proportion of the program that can be parallelized and N stands for the number of processors. Okay, next we're going to apply the Amdahl's law for the Snapdragon 8 Gen 3. So let's consider P equal 0.7 and N equal 8. So let's plug in this value into Amdahl's law. Okay, so first S equal 1 divide by bracket 1 minus 0.7 which is P plus 0.7 over 8 which is N. Next S equal 1 divide by 0.3 plus 0.0875. Next S equal 1 over 0.3875. So the final answer is 2.58. So the conclusion is this indicates that the program might execute around 2.58 times quicker than it would with a single processor in an ideal world where all parallelizable jobs can be evenly split among 8 processors, accounting for the sequential portion as well. Okay, so we're going to the next part, which is identify bottlenecks and propose strategy for leveraging parallelism to improve performance. So first of all, how to identify bottlenecks? Here are 2 ways to identify bottlenecks, which is examine the program sequential section to determine the location of the bottleneck. The part that cannot be parallelized are this one. And the last one, profiling tools can assist in identifying the precise code segments that take up the most time. So the next part is strategy for leveraging parallelism. Here are 5 strategies, which is task parallelism, data parallelism, algorithm enhancement, the utilization of SIMD, and the last one, optimization. So the first one is task parallelism. It can divide the program into manageable chunks that can run on separate cores in parallel. Next, data parallelism. It can distribute data among several cores and concurrently execute the same operation on every subset of data. For algorithm enhancement, it can investigate technique that minimize the sequential section of the program by naturally taking advantage of parallelism. Next, the utilization of SIMD. It can enable the processing of many data components in parallel with a single command. And the last one, optimization. Parallel performance can also be enhanced via optimization strategy like cache, memory access, and loop parallelism.